extension for this unit is just going to be in the way that you write your final answers. If you're working on really getting a hold of the algebra and the trig and the unit circle values, then you should absolutely focus on that. That's the most important part. If you're ready to do a little bit more, this extension is for you. So this is what you would do if you were asked for the general formula for all solutions instead of just the solutions that are on the unit circle, which is what we went over in class. So if you're asked for the general formula for all solutions, if the two angles create the same line on the unit circle, you're going to keep the smaller angle and add a plus 2 pi k after that angle. And I will obviously show you some examples of this. What the plus 2 pi k gives you is half a rotation on the unit circle. So if 0 is a solution, plus pi k is going to get you to pi. And plus pi k is going to get you to 0 or to 2 pi. And that's going to work for positive rotations and negative rotations. So that's why we call this the general formula for all solutions, because it not only captures the solutions that are on the unit circle, but it also captures all of the coterminal angles. And you guys know from the unit circle unit that there are an infinite number of those. Plus 2 pi k is what we use when they're not right across from the unit circle from each other. So if just 0 was your solution, when we do plus 2 pi k, that gives us all the way around the positive direction or the negative direction. All right, so let's do some examples. 1 through 8 down here on the bottom, the reason you don't have a ton of room is because these are all these are the examples from the top that we've already solved. So what I did is I just copied my work from the top so that we could look at it down here and just rewrite our solutions. Something to think about, or something that you'll notice when we're doing this plus pi k and plus 2 pi k, you're going to use plus pi k most often with tangent, with cotangent, or when you do the plus and minus. If your solutions are plus and minus radical 2 over 2, or plus and minus 1. For plus 2 pi k, you're going to do those in all your other situations. Sine, cosine, most often secant, and cosecant is when you're going to use those, as long as you haven't forced that square root. Okay, so let's do some examples. So we solved tangent of theta plus pi, or plus radical 3 equals 0 up top, and we got 2 pi over 3 and 5 pi over 3. If you're doing this extension, the first thing I would do is draw a picture of those solutions. So 2 pi over 3 is in quadrant 2, and 5 pi over 3 is in quadrant 4. Those, not a pretty picture that I made, but those two make a straight line. So this is our first situation there. We're going to capture that first angle, and we're going to say plus pi k, because that second solution on our unit circle is pi away. A straight line on our unit circle is pi units. So we're going pi to get there, and pi to get back. And again, that k is an integer, so it's positive or negative whole number, and that just gives those rotations for you. So that's your first example. Again, draw your line and then decide, do I need plus pi k or plus 2 pi k? Or draw your little picture. Number 2, again, all of these are problems we solved earlier. We have cosine equals 1/2, so that's pi over 3 and 5 pi over 3. So here's my little diagram. Pi over 3 is in the first quadrant, and 5 pi over 3 is in the fourth quadrant. Those do not make a straight line, those two angles together. They are not pi apart. So what we're going to need to do is write two equations as our answer. Pi over 3 plus 2 pi k gets us all the way around the unit circle and back to pi over 3 in the positive and negative direction. And 5 pi over 3 plus 2 pi k captures all of the coterminal angles for 5 pi over 3. All right, I'm going to keep rolling. Again, I think you just drawing the picture is the best way to go here. 7 pi over 6 and 11 pi over 6 were our solutions for number 3 up above. So again, draw your picture. 7 pi over 6 is in quadrant 3. 11 pi over 6 is in quadrant 4. Those don't make a straight line. They're not right across the unit circle from each other, so they are not pi apart. So what we're doing here is writing two equations. 7 pi over 6 plus 2 pi k captures all of your coterminal angles for 7 pi over 6, and 11 pi over 6 plus 2 pi k captures all your coterminal angles for 11 pi over 6. All right. The pi over 4, sometimes it seems like you should be able to do more than you can. So when you see pi over 4, don't think that you can write a simpler equation. I'm going to label them just like I did in my last. Pi over 4 is in the first quadrant. 3 pi over 4 is in the second quadrant. So again, those make a V, not a straight line. So we're going to need to write two equations. There is no simpler way to do this. I know it seems like there should be, but there isn't. So pi over 4 plus 2 pi k is going to get us all of the coterminal angles for pi over 4 and 3 pi over 4 plus 2 pi k is going to get you all of your coterminal angles for 3 pi over 4. The next two problems are problems where we had to take the square root. And here we were really careful in class to make sure we did that plus and minus situation. And that is really going to help us writing these equations as well. So we have all the pi over 6's for this one. And you want to be careful here how you group these. So when I'm writing my equations here, you definitely have straight lines going on. When I'm writing my equations here, pi over 6 is the smallest angle. I know I'm going to be able to use plus pi k because 7 pi over 6 is on that same line. So those two are pi apart. So pi over 6 takes care of pi over 6 and plus pi k, 7 pi over 6. And then I'm going to do the same kind of thing for 5 pi over 6 is the next smallest angle. If I do plus pi k there, that's going to capture that 11 pi over 6 angle. So I've seen students do this with some success. They're just checking off which angles plus pi k take care of each other. You do that every other situation. Go ahead and pause the video and try number 6. All right, let's take a look. So again, we have all of the pi over 6's. So how does it work when we have all of the pi over 6's? We have one equation for pi over 6 plus pi k, and again, that's going to take care of pi over 6 and 7 pi over 6. We have the equation for 5 pi over 6 plus pi k, and that takes care of those other two. All right, two more situations here. This problem, so this was a factoring problem. Especially when we're doing GCF, sometimes our factoring problems are going to look kind of random. Our solutions are going to be kind of crazy. So you almost might want to do two little diagrams. One for your 0 and pi, and then another for 7 pi over 6 and 11 pi over 6. If you can handle all of them on one, that's fine as well. But I think sometimes looking at those separately helps. So for this guy, 0 and pi are absolutely on the same line. So we can capture that solution by just doing 0 plus pi k that gets you 0 and pi in one equation. 7 pi over 6 and 11 pi over 6 are not right across the unit circle from each other, so we're going to need two equations for those, two separate equations. Again, you're looking for that v, and that v, really in any direction, is telling me plus 2 pi k. 7 pi over 6 plus 2 pi k, and 11 pi over 6 plus 2 pi k. And that's how you write those equations. Last one, another problem with some GCFs. Again, we have that same 0 and pi situation. And here we have pi over 3 and 5 pi over 3. So pi over 3 is in quadrant 1, and 5 pi over 3 is in quadrant 4. So for 0 and pi, here are equations. 0 plus pi k, those make that straight line. They're pi apart. That gives me those two. And pi over 3 and 5 pi over 3 are going to need separate equations. And again, the 2 pi k and the pi k just capture all your coterminal angles that are positive and negative rotations around the unit circle, of which there are an infinite number. Okay, I hope that was really helpful. Please let me know if you have questions.